Good afternoon. Is this? Good afternoon. Is this working?
Yes, yes.
Okay, fine. So, good afternoon. I am Radhika, a PhD student in the Quantum Optics and Entanglement Lab in the Department of Physics, which is being led by Professor Anand Kumar Jha. And in this talk, I would be talking about structuring correlations of entangled photons. So, before we proceed, we need to know how to generate entangled photons. So there is a process called spontaneous parametric down conversion, which is used to generate entangled photons. And in this, we have a nonlinear crystal, and a pump beam is incident on this crystal. And what happens is that the pump photon gets destroyed, giving rise to two new down converted photons known as the signal and the idler photon. And these photons are entangled in various degrees of freedom, like position momentum, uh, time frequency, polarization, etc. But our focus would be on the position momentum basis. Energy as well as momentum is conserved in this process. However, if the wave vectors do not match up perfectly, then there is a delta kz mismatch. And this delta kz mismatch basically decreases the efficiency of this process of generating the entangled photons. Now, the crystal's optic axis and the pump beam's propagation direction, they make an angle theta p, which is known as the phase matching angle. And delta kz mismatch parameter is essentially a function of this theta p, the phase matching angle. Now, there is a certain nomenclature for phase matching conditions, which is as follows, that if both the down converted entangled photons move in the same direction, then we call it collinear phase matching. Whereas if they move in different directions, it is called non-collinear phase matching. So this collinear to non-collinear transition happens when we increase theta p. So now we want to know how we mathematically represent the state of these entangled photons. So here is this big expression. It might look very complicated, but what we see is that this state, the entangled state in the momentum basis, is essentially a product of two quantities, V and phi. So V is the pump field amplitude, so that pump beam which is incident on the crystal, and phi is the phase matching function. So pump field amplitude is basically a Gaussian beam, and this phase matching function is basically a function of the delta kz mismatch, which in turn depends on theta p, the angle between the crystal's optic axis and the pump propagation direction. So when I said that the title of my talk is structuring the correlations in the entangled state, so this is the entangled state, and now we will move to how to structure these entangled states. So in order to understand the structuring of these states, we need to know about two terms. The first one is the coincidence count rate. So this is the probability of detecting the idler photon at a location Ri and simultaneously detecting the signal photon at location Rs. So this simultaneously word is very important. So detecting both the photons together or in coincidence is known as the coincidence count rate. So this is how the distribution looks like, and this shape of the diagonal represents strong correlations between these photons. So the photons have maximum probability of being detected along that diagonal and zero elsewhere. The other term is the conditional detection probability. So this is the probability of detecting the signal photon at location Rs, given that the idler has already been located or detected at the location Ri0. So it is essentially a distribution of the signal photon around the idler photon. And this is how it looks. It looks like a blob very close to the crystal. So when I say that I want to structure the entangled state, it essentially means that I want to either structure this diagonal or this blob. But exactly why are we even interested in structuring these correlations, as I call it? That is because there are some useful applications of structured spatial correlations. So in the classical sense, it has been shown that having structured spatial correlations could lead to enhanced resolution imaging. That is, one can actually beat the Rayleigh limit of resolution by using structured spatial correlations. So we want to see if our quantum correlations could also be beneficial in this domain. And there are certain quantum imaging techniques and ghost imaging techniques where using photons from the down conversion process could actually have better signal to noise ratio and provide better noise robustness. So this is the motivation behind trying to structure spatial correlations in these entangled photons. So experimentally, how do we detect these correlations? Well, the conventional coincidence technique involves using two detectors, which is very cumbersome and tedious process and almost impossible to get a 2D structure out of using two detectors. So our technique involves using only one detector, that is one EMCCD camera. So if you want to see in the position basis, we will use two lenses. In the momentum basis, we use only one lenses. So the important thing over here is that only one detector, that is one EMCCD camera is being used. And we will record millions of images, millions of intensity profiles from this camera and reconstruct the correlation information or the correlation structure from them. So these are some of our numerical simulations and experimental results of the correlations that we have seen. So this is for the coincidence count rate. So you see that as theta p increases, so theta p increases means moving from collinear to the non-collinear regime, then we see that the diagonal of the correlations splits up into two diagonals and the spacing between those diagonals increases. And we see a very good match between our theory and our experiment. And these structures on the right in the non-collinear regime are actually new structures, and these have not yet been reported in the existing literature. So this is for the coincidence count. We can also see in the conditional probability distribution. So what happens in the conditional probability distribution is that we have a blob in the collinear regime, and as theta p increases or as non-collinearity increases, we see that this blob opens up into a ring and becomes a bigger and bigger ring. And again, these ring-like structures are new structures not yet reported. Now the question comes, are these the only kind of structures that we can generate, like a blob becoming a ring, a diagonal becoming two diagonals? So turns out that we can actually get much richer structure provided we use two crystals instead of just one crystal. So these are the results for using two crystals which are separated by a certain distance, and we see that as the spacing between the crystals increases, we see more and more rings or more and more fringe-like structure, and these are extremely rich structure. And again, we see that experimentally also we are able to reconstruct these structures, and there is a very good match between our theory and our experiment. One clarification I want to provide is between the single photon intensity and the two photon correlations that I have shown. So these rich structures on the right side are in the two photon correlations. It is not in the single photon intensity. So single photon intensity is what is captured by this EMCCD camera. So if you just place the camera and you observe what you see on the camera, you will see a blob irrespective of what your phase matching conditions are. Whereas if you look at the two photon correlations or the conditional probability distribution, then you see all these nice kind of ring-like or fringe-like structures coming up. And I've always been talking about entanglement, that our photons possess entanglement. So how do you certify or how do you say that certain photons are entangled? Well, that is by using certain kinds of entanglement witness. Over here, we have used EPR correlation and entanglement of formation. So simply put, we have the momentum distribution and the position distribution. And if we find out the widths of them, and if we take the product of the widths, this is this product, delta K times delta X. And if this product turns out to be less than 0.5, then we say that the state is entangled. Similarly, if the entanglement of formation is positive, then we say that our state is entangled. So we have, to conclude, we have shown that we have generated new kinds of structure in the two photon correlations, and these two photon states are definitely entangled. And the future work in this direction would be to explore the applications that I mentioned, that is enhancing the resolution and trying to use the entanglement present in this state and try to basically see if they offer some extra benefits. So thank you very much. Yes.
Describe that, and why is it necessary in your experiment to have kind of
Okay, so as I mentioned in this, so this is for witnessing the entanglement. So in order to say that something is entangled, you need in the conjugate basis. So you need to measure in any conjugate basis. So position, momentum are conjugate basis. So you need to measure the width both in the position and the momentum basis, and only then can you say that something is entangled. Similarly, time and frequency. So these are also conjugate basis. So if you want to say that my state is entangled in the time frequency basis, you have to make a measurement in the time basis as well as in the frequency basis.
So let's figure once again for this.